All right, so today we're going to start on the last module, the last major portion of this course, which is trees and tree-based data structures. And we'll progressively create this data structures out of these trees after we've gotten some terminology down that may or may not be a retread of things that you've seen in other courses, graph theory and stuff like that. So remember that we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube live stream. But otherwise, what our goal has been in the last couple of modules has been to develop data structures in which you can hold data, and it offers you efficient operations. Remember, CRUD operations: create, retrieve, update, and destroy. So our ultimate goal is that we want a perfect data structure. We want one data structure that will be efficient in all use cases forever and ever and ever. There is no such data structure. We like data structures because they have structure that we can exploit. Sometimes we can exploit that structure in some applications, and other times it becomes that structure is not so good in that application. But our ultimate motivation is to get something that is all around good for the basic CRUD operations of retrieve, update and destroy, or in this case, retrieve and search, insertion and deletion. Because what is an update? An update is nothing more than a retrieval. You delete it, and then you insert the replacement for it. So we'll keep our attention to these three basic operations. Now let's look at what we've already done in this course. For example, linked lists. Right? Lists. There we go. In one situation, they were very, very good, and in another situation, they were very, very bad. The situation in which they were very, very good was insertion or deletion from the head or tail. Right? Now that we have some algorithm analysis under our belt, what was the complexity of those operations? That is, what is the big O of those those operations? With a linked list, if you've got this list, simply creating a node and then appending it to the front of the list, that's going to be a constant time operation, right? Order 1, constant. On the other hand, a different situation in which that structure cannot be exploited for efficient operations is going to be an arbitrary insertion or index-based find or search operation, right? That ended up being order n, right? A linear amount of time or a linear amount of operations. Remember the lazy painter or the maliciously compliant painter that didn't pick up their bucket and had to go back and forth and back and forth. With a linked list, if you want an arbitrary operation of, say, I want to insert something right in the middle, unlike an array where I can jump to the middle, right? I have to start at the beginning and I have to traverse to the middle to do something with it. That all gets flipped on its head when you look at an array-based list. The same exact operations of, say, insertion or deletion at the front, that now becomes an order n operation, or a linear time operation. Why? Because you have to shift everything down to make room for it, right? Note here that if you want to insert it at the tail, that is a free operation. That is a constant time operation because you just have to jump there and then put it there. Unless, of course, you have to expand the size of the list, in which case it becomes a linear time operation again. But an arbitrary insertion, or let me go ahead and rephrase that. An arbitrary index-based search. Because we have random access, that's going to end up being a constant time operation due to random access. Random access being that you've got everything stored in a memory location. You know exactly where it is and how to compute that memory offset and jump to that memory location. There could be some underlying details like a cache miss or something like that where you have to load something up into main memory. But ultimately, at the end of the day, with respect to the size of the list, it's going to be a constant time operation. We also saw stacks and queues. Right? Stacks and queues had efficient push, pop, or NQ, DQ operations, which were order 1, right, with the proper implementation. But their structure came from the restricted access. With a stack, we didn't allow an arbitrary access, right? If you've got a stack of dishes, we're not going to allow you to arbitrarily insert a plate or remove a plate from the bottom. By restricting the access, that's where we're giving structure. We're giving structure to the behavior of the algorithm, or of the data structure, in how you access it and how you access its members, right? We're restricting you in some way to give more structure to the data structure. Another one would be searching on array, if sorted, right? How could we exploit that? If an array is sorted, what search can we use to have really, really efficient operations? Binary search. Binary search offered order log n search operations, right? That's really as good as it gets, right? There is this magical data structure out there that offers amortized constant time for everything. It's called a hash table. It goes beyond the scope of this course, though, so don't worry about it yet, right? What I want to do is that's our ultimate goal. Ultimate goal is efficient operations for all basic operations, right? And the solution that we're going to look at least for the rest of the semester, are trees, right? Trees, they provide a potential for efficient operations, all three, right? Now, I say potential here because we're not even going to get to the point where we have a guarantee on its behavior. We're just going to look at the basic data structure itself, right? So first of all, we need to know what trees are. Trees are graphs. What is a graph? A graph is not, like the graphs that we were doing with respect to efficiency of time versus number of comparisons or something like that. Input size versus time or something, where we graph this n squared algorithm or whatever. A graph in this sense is a collection of nodes, right, or vertices, right, and edges. So you've probably seen graphs before. You might even be discussing them right now in, say, 235. Yes? No? Earlier? Okay. Why do we call them nodes instead of vertices in the context of this course? It's because you're going to be storing data in those vertices rather than just labels. And so we call them nodes. It's really, it's just a small technical detail, right? So what's an example of a graph? Here you go, right? What are the vertices? A, B, C, D, E, F, and G. So it's got 7 vertices. It's got a whole bunch of edges. Edges connect single pairs of vertices. Now this is an undirected graph. So the vertex or the edge connecting A to F, AF as an edge is the same thing as FA. Right? And we just usually write, we write it like that, right? They're ordered pairs in general. But in the context of undirected graphs, they're the same thing. Okay? Get rid of that. What is an example of a pair that's not connected? AC, right? AB are not connected by a single edge. Now there is a path from, say, A to B. How can we get from A to B? AEB, right? That would be a path of length 2. Is there an alternative path? A, D to B, right? There's a path of length 2. Is there a longer path? A to F, E, B, that's a path of length 3, right? What about this path? The path that goes from A to F to E to G to D to F to E and then to B. That's a path. But it goes back on itself, and so we don't consider those things, right? We only consider what are called simple paths, right? Vertices or nodes can be connected by a path, right? For our purposes, all paths will be simple paths, right? They will not visit the same vertex, nor the same edge, nor traverse the same edge more than once. Okay? What's the length of a path? The length of a path is the number of edges along it. Okay? Now, we said that A and C are not connected, so is A, C, F, is that a valid path? No. Right? You can't go from A to C and then over to F. You can go from C to F, but that's not, the first pair of vertices is not there. Okay? So a path is a sequence of ordered vertices. A cycle is a path that starts and ends at the same vertex. Okay? So, for example, over here, give me an example of a cycle starting at A. A, D, F, A. There we go. What's the length of that path? 1, 2, 3. Right? What's another example? Is there a longer path, cycle? A to E, G. Ooh, wow, okay, I can do that. Then what? D, F, A. That's a simple cycle, right? And it is of length what? 1, 2, 3, 4, 5. Okay. The length of a path, if the length of a path is 5, how many edges are on, or how many vertices are on it? 1, 2, 3, 4, 5, 6, because you need the endpoints. If you've got a if you've got a cycle of length 5, how many vertices are on it? 1, 2, 3, 4, 5, right? Because you start and end at the same vertex. Okay. All right. So that's just some basic graph terminology here. Okay. So once we know what a cycle is, then what is a tree? A tree is an acyclic graph. A graph without cycles. Right? And it's as simple as that. Right? So let's make some observations here. Right? Oops, let's go ahead and go with this. Right? If a graph, or if a tree is connected, right, then and has n vertices, how many edges does it have? Right? So let's come over here and let's first observe, is this this is a graph certainly, but is it a tree? No. No. Why? Because it has cycles. We already identified several of them. So let me go ahead and draw an actual tree here now. A, B, C, D, E, F, and say G. Right? There is a tree. Is there any cycle there? Nope. If I were to draw one more edge here, there would be a cycle, right? Not necessarily that edge, but I could also draw, say, this edge. Is there a cycle now? Yeah, A, B, D, E, F, A, right? So there are 1, 2, 3, 4, 5, 6, 7 vertices here. Necessarily how many edges then? 1, 2, 3, 4, 5, 6, right? Same thing as a path, right? Where if there are, the answer is going to be that there are n minus 1 vertices. Or sorry, edges, right? Of course, by definition, there are no cycles. If a tree is disconnected, right, then it has multiple connected components, and is called a. What happens when you have more than one tree? What happens in real life when you have many trees? You have a forest. All right. And so we have a very low threshold here. As long as you have 2 trees, A, B, C, D, F, G, H, oops, H, I, J. There we go. Once we have 2 trees in one single graph that are disconnected, then we have a forest. You could, of course, have another tree, I, J, K, L, and you could have even a isolated vertex over here, which is in the context of trees, we sometimes call these seeds, right? But if this is all one big giant graph here, you have 4 connected components. 1, 2, 3, 4. They're all disconnected because there's no path from A to say H or I or J, right? That is a forest. We're also not going to look at forests, right? We will assume that all of our trees are connected. Right? You can talk about forests, but we're not going to. Okay. Let's see. The length of a path or cycle is the number of edges along it, right? And that's all that we need as a basis for terminology here to get into trees, okay? In fact, what we're going to do is we're going to add a little bit more structure. So as we're going along here, right, a graph, everything is a graph, right? A graph is as general as it gets. Usually when I cover graph theory in, say, 235 or something like that, I ask, why do we care about graphs? It's because graphs can model anything, right? Because graphs are nothing more than a relation. Have you talked about relations, binary relations on a set, right? That are reflexive, irreflexive, transitive, symmetric, etc., right? Well, what is a relation? A relation is nothing more than a graph. And a relation can model anything, right? We've seen this already. A UML diagram, what is it? A graph. An ER diagram, what is it? A graph, right? In fact, both of those are not necessarily trees, but a UML diagram in Java is definitely a tree, right? Because you only have a single inheritance hierarchy. In C++, it would be a lattice and that kind of thing. Yeah?
For our UML diagram, are we only supposed to have, like, the entities?
It'd be good if you split it up. So focus on your assets right here, right, and show the asset hierarchy, and then all the other. Here's the person hierarchy.
I mean, like, we just not put like the class is like an account report and stuff like that.
You can put those off to a third diagram if you split it up into multiple diagrams, right? That allows you to focus only on one part of the system. But certainly, those things are going to have some sort of relationship, not an inheritance relationship, but I use this class over here relationship. Right? Right. All right, so what we're going to do is we're going to add more structure to this. Graphs are just general. I'm going to restrict graphs even further to trees to give them more structure. What is that structure? You don't have any cycles, right? And by the way, what does that mean as far as the number of paths between any two things, right? So if I've got A here, and again, let's only consider trees now. So this stuff is gone. I've got a single tree here. From A to any other node in this tree, how many paths are there? How many unique, simple paths are there? What about to F? A to B, to D, to E, to F. Is there any others? No. Why? What if there were? It'd be a cycle, exactly. If you've got a path going through the tree, but then you had this other path over here, guess what? You formed a cycle. Right? So one of the key characteristics of a tree is that from any node to any other node, there is exactly one path. We're not talking about a forest where there might be 0 paths. We're talking about a connected tree where there's exactly one path. That's more structure. Now what I'm going to do is I'm going to further give it structure by orienting it. Binary trees. Right? You can orient trees in a top, down, left to right manner. Right? What does that mean? Well, let me take this tree. Right? There are several different orientations that you can do here, but for imagination purposes here, suppose that I grabbed D, the node, and then I held it up here in 3 space, and then I shook it, and all of the nodes fell down because of gravity. What would it look like? Oops. D would be up here at the top, right? Because gravity goes down, and it's connected to B, E, and G. B, E, and G. Why did I orient it in that left to right manner there? B, E, G, it's in alphabetic order, right? Why? That's the natural order of things, right? We as humans want to organize things to make it more readable, right? In fact, if you read this, it's going to be read top to bottom, left to right. Okay? Off of B, B is connected to A and C. So after we've dangled it and shook it and let gravity take over, we've got those vertices. E is connected to F, and G is just hanging out all by itself. Right? So this is the top, and this is the bottom. Okay? That's not the only orientation. What if I did it from another vertex? What if I did it from A, right, and shook it? It would look something like this. A goes down to B. B is connected to D and C. Right? And C, that's where it ends. But D is connected to E and G. And E is connected to F. And it looks like that. Okay? So I have an orientation top to bottom, left to right. Right? That's more structure. Now let's add another structure. Right? But first of all, some terminology. Right? The node at the top is the root element. Root node. Right? Nodes at the bottom are, well, if the root is up here, in a real tree, a root is down here, right? And what's at the other end? Leaves. Are leaves. Right? It's oriented in top to bottom manner, so you can also speak about a parent-child relationship. Right? For example, in this particular orientation right here, A is the parent of B. Right? B is the child of A. Right? Not only that, but you can talk about, the left to right orientation of children. This is the leftmost child. This is the rightmost child. You can call this the middle child, right? And it resembles now a family tree. Family trees grow down. Computer science trees grow down. And they have for 200 or 300 years or whenever it was that Cayley first wrote his first paper on it. Why do our trees grow down when natural trees grow up? Right? Because we like to read things in a top to bottom, left to right manner. Right? That's that's how most Western languages are. Okay. And because we are putting data into our trees, that's how we'll want to be oriented. Okay. Now what I'm going to do is I'm going to further restrict this. Right? Suppose you have another restriction. Right? For each node, there is at most 2 children, a left child and a right child. You still have a parent, potentially, except for the case of the root, which has no parent. So in other words, i.e., you can have a left child and no right child. Vice versa, you can have a right child and no left child, or you can have no children, or both children, or both. A node with no children is as we already defined it, a leaf node. There we go. Okay. So let's take a look at a much larger example here now. There's my binary tree. Okay. So the root node here is A. What are the leaves? L, R. Is M a leaf? Nope, because it has a left child. Right? H is not a leaf because it has a right child but no left child. Right? What else? N, O, P, Q, and K. Right? Those are all leaves. In fact, if we want to, we can highlight those as leaves. There's all the leaves. Did I get them all? Yep. Good. Now, we can also talk about the depth of a tree. Right? So what is the depth of each node here? Depth, right here. Node and its depth. So here's more terminology here. What about B and C? The depth of a node is the length of the unique path from the root to that node. So B here, to get there from A, only requires a path of length 1. So its depth is 1. Likewise, C is 1. And you can kind of see why I wrote it in a left to right manner with all nodes that have the same depth are on the same level. For example, D, E, F. What is their depth? 2. Why? Because you go from the root to any one of those nodes in the second level here, and it's 1, 2, or 1, 2, or 1, 2. Right? Likewise, what about G, H, I, J, and K? What are its depths? 3. Right? And then the other ones, L, M, N, O, P, Q, are all going to have depth 4. And what about R? Depth 5, Y, 1, 2, 3, 4, 5. The length of the path, unique path from the root to that node. Right? What about, and I skipped it on purpose, what about A? What is the length of the unique path from A to A? 0. And so it has a depth of 0. What is the depth of a tree itself? Tree depth. The depth of a tree is going to be the maximum of any of its nodes, of the depth of any of its nodes. So what's the maximum in this case? 5. So the depth of this entire tree is 5. Right? Let's go ahead and note that. Right? The depth of a node is the length of the unique path from the root to that node. Right? The depth of a tree itself is the maximal depth of any node. So you can have a tree of depth 0. That's that seed where it's only one vertex. You can also have a tree of depth -1. Right? What would that look like? There it is. An empty tree has depth -1 by convention. Right? Once I have one vertex right here, that is going to have a depth of 0. Right? And so if I don't have any vertices, all right, then it's going to be of depth -1. Okay. All right. So why does all of this matter? Right? Suppose you have a full binary tree, right? That is, every child exists except for at the last level, which are all leaves. Okay. How many nodes are in such a tree of depth D? All right. Once we have an answer to that question, then I'm going to flip the question around and ask, if we have a certain number of nodes, how can we fit that into a tree of a certain depth? Okay. So we'll just do this visually here. So suppose that I only have one node. I have one node tree, right? What is its depth? Again, it's 0. But what is the total number of nodes? Of nodes at depth. So what's the total number of nodes at this first depth? Just 1. As I expand this out and I have the condition that it's a full binary tree, then I'm going to have both children. So depth 1 now. Depth 1, we're going to have 2 nodes at that depth. And you can kind of see that this is going to be an exponential blow up here. At depth 2, we have 4 nodes. And what's the pattern? At the next depth, we have how many? 8, ... If I were at depth k, how many nodes am I going to have? 2 to the k. So if I told you that you went all the way down to depth d, right, it was just this big giant tree here, ... to d. At that particular depth, you're going to have 2 to the d nodes. So what is the grand total here? Right? What is the grand total of all nodes? This is a pretty simple series here, a finite series, right? Which is a summation. N, which is the number of nodes here, is going to be the summation of, and what did I use, k? Yeah. K is starting from 0 up to D, right? Why 0? Because remember that we start at depth 0 and we go up to depth D here. And we're going to be summing up powers of 2, 2 to the K. Again, this was 1 plus 2 plus 4 plus 8 plus ... up to 2 to the D. What's the closed form solution of that series? In general, if it was K equals 0 up to D of X to the K, does anybody know the general form solution of that? I think it's X to the K plus 1 minus 1 all over X minus 1. Something like that. Don't quote me on that. That's why I'm going to erase it. But this simplifies to 2 to the D plus 1 minus 1. Right? And this shows up all over the place, especially in computer science. Why? What if you summed up all of the binary numbers with n bits, or with d bits? Right? That's going to give you the maximum representable value like that. So if d was 31, you would end up with 2.147 billion. Right? 2 to the 31st minus 1. Okay. All right. Let's see. All right, there. Yeah. So in other words, we get at the end n to the d plus 1 minus 1. That's the number of nodes in a full binary tree. Okay. Now I'm going to flip it around. I'm going to say, suppose that you had n nodes. What's the depth if it were almost full, if it were full? Right? So given a tree, a binary tree, with n nodes, and it is full, so here, given a full binary tree with n nodes, what is its depth? In other words, we're just going to take this and solve for d. So I'll take 1 onto the other side. N plus 1 is equal to 2 to the d plus 1. Right. How do I get rid of that 2 to solve for d? Log base 2, implicit, is going to equal to d plus 1, so I'll subtract 1 immediately and get d is equal to log base 2 of n plus 1 minus 1. Tell me what that is in big O notation. Log n. Right. Again, I'm just ignoring this lower order term and ignoring this constant right here. Right. So it's going to be order log n. That seems familiar. Where have we seen that kind of behavior out of an algorithm before? Binary search. Binary tree. I wonder if there's a connection there. Right. Here's the connection. Go back to, nope, that's not what I want. I want to go with a sorted array. Here we go. All right. So to exploit binary search, if we had a sorted array and random access, what can we do? We can jump to the middle and say, oh, this is the thing I'm looking for because I was searching for 12, or that's not the thing I'm looking for because I'm searching for 83. That means that I need to go to the left, to the right. In either case, I've cut it in half. If I want to search for something smaller, I go to the left, right? But that means that I have to have random access. Can I do that with a linked list? Nope, because you can't jump into the middle of a linked list. But what would this look like stored as a binary tree if it were sorted already? 12, what if I promoted that up to be my root element? Right? And then I have a left subtree and a right subtree containing everything from -3 up to, what is it, 9? And over here, everything from 34 up to 180. Right? And then I continue that process, right? What if I stored, say, the middle element here, 4, and then I had 2 trees hanging off of that? Right? And then same thing on the other side, 101, or 102, excuse me, and 2 trees hanging off of that. Right? Now do I need random access anymore? Nope. You start at the node and you ask yourself, is this what I'm searching for? 12. Okay, I'm done. Otherwise, I can go left and I can go right. Or I could go right. Right? In either case, I've cut it in half, just like binary search. Right? Assuming that there are an equal number of elements over here and an equal number of elements over here. In other words, it looks like a full binary tree. Not necessarily the case, unfortunately. Why? What if it looked instead like this? It was, I don't remember what the numbers were, but let's just go ahead and go with this. Actually, no. 10, 20, 30, 40, ... all the way up to 100 here. Now there are 10 nodes here, 10 through 100, right, by tens. Right? I'm not going to pull a trick and say, oh, actually there are secretly a million nodes in here. Right? Right? There's a pattern. Right? What's the depth on this tree? Well, there are 10 nodes, so in between is going to be 9. Right? In general, for a binary tree, it could be as bad as order n. In other words, what is this thing right here? It's a line. If I depicted it like this with arrows, does it look familiar? What is it? It's a linked list, right? It's skewed, right? It's a skewed tree, which is a linked list. Right? So what we're doing is we're kind of developing an in-between kind of data structure. We're developing something that we could potentially have the ability to do a binary search and cut the search space in half each time. Unfortunately, it looks, in the worst case, it looks kind of like a linked list, in which case we are stuck because we don't have random access to jump to the middle immediately. Okay. All right. So, but it does offer potential, right? If we can develop a binary tree such that the three basic operations are proportional to the depth of the tree, and we can guarantee the depth is order log n, then we've achieved our goal. We can put stuff in, we can find stuff, and we can delete stuff all efficiently, order log n, just like binary search. But for everything, not just search, but also put stuff in and take stuff out, deletion, right? I can get you this far, right, in this course. And this is all the further we're going. We're going to talk about basic operations, and they're all going to be proportional to the depth. Unfortunately, I can't get you this far. I will not be able to guarantee you that the depth is going to be logarithmic. Don't worry, when you take Computer Science 3, say, you'll talk about balanced binary search trees that automatically reorient themselves so that if it becomes too skewed to one side, it rebalances to the other side. Again, beyond the scope of this course. What I want to do is I want to focus on the basics, okay? All right. Let's see. So let's talk about the next part here, implementations in, say, Java, okay? And let's go over here. Suggestions on how to do this. Okay, what is the root? A node, okay. Is it like we did with a linked list and it's a list node? Nope, it's going to be a tree node. And I will immediately parameterize it because I learned my lesson last time. I don't just want a linked list for integers. I want a linked list to be applied polymorphically to any type. And so I want a tree node and a tree that can store any type of data here. This is one node now. This is not the entire tree. This is just one node. If we focused on that one node, what characteristics do we have here? Oops. We have the piece of data inside, right? We call that the key, right? Or the piece of data or the item or something like that. What other relations do we have? If this were a linked list, I would have next. This is not a linked list. Instead, what do I have? A left and a right child. Right? What else might I want? Parent? Good. Why? Because just like a linked list, right? A linked list has next, right? A doubly linked list may be a little bit more convenient, allowing us to go both ways, right? This way, it's only a one-way trip. You can't traverse back. But if we had both ways, a next and a previous, and we also had a left child and a right child, and we can go back up to the parent, right? That seems a lot more convenient. Okay? So let's go ahead and put those in there. Private final T, and I'll just call it item. Right? That's the actual piece of data that I'm going to be storing in the node. Right? And it's of type T. Right? And then private, I'm not going to make it final because I might want to change the topology of my tree. If I just create a node, of course I'm going to need to be able to set the left child, set the right child, set the parent if I want to reorient stuff, just like I did with a linked list. We made the item final, but we didn't make the next node final because then that would mean that we can never change the list orientation. Right? So I'll make it into another tree node. T, left child, parent first. What else? I'll say left child and right child. Okay. We do need at least one constructor here. And I will go ahead and just do it with the item here. So you can give me the item and I've created a node for you now. Okay. But otherwise it's up to you to set or get the left child and the right child and the parent. So let's go ahead and generate those. Getters and setters. I'll generate the getters and setters. Here, let's expand all. Actually, though, let's just select all. And then I want them all in this case, except for... Oh, okay, good. It was smart enough not to generate the set item because it was final, right? But I want everything. Why? Because I want to be able to get and set the parent because I want to reorganize the tree, potentially. Right? There, that's one tree node. Do I yet have a tree? No. Nope. Just like a linked list node didn't define a list, instead we needed another class. New class tree. I'll call it binary tree. If it were just a tree, it could have 5 children or 10 children or whatever. This is a binary tree because it has a binary tree node. I should have called it binary tree node because it only has left and right, but that's okay. All right, how do I represent an actual tree? Where do I get started in all of this representation here? At the root, right? Why don't I keep track of everything? Why don't I keep a list of all of the tree nodes? All nodes. Now I'm back at the beginning now, right? I've got a list data structure, not a tree data structure. So nope. So private, final or not? No, you want to change the root maybe, right? Tree node T root. There we go. Okay. I'm going to go ahead and create a constructor here with the root. Yeah, I'll go ahead and generate it. So you're responsible for creating a tree node and giving it to me and initializing that as the root. Another option would be, of course, if you wanted a public binary tree, an element, you give me the element item, and I'll go ahead and create a root node for you. Right? If you wanted both of these, that's fine too, right? You would have a tree node, T, new root is equal to new tree node of the item, and then this new root. There. Okay. That's because it did that before. I don't know why. Why would you want a private constructor by default? I don't know. Did it here too. Public, public, public. There we go. And you should be able to infer the type. Why are you complaining? Oh, okay, fine. I won't be able to do that. I'll just go ahead and go with this then. This dot root is equal to. If you're going to call another constructor, it has to be the first thing you do, because it can't be in an intermediate state. Right? It has to be constructed before you can talk about it. Right? But otherwise, that's good. That's flexible. Okay. Let's go ahead and create this one. Right? At least part of it. I'm not going to create all of it.
We want public constructor where there's like, can we give it a node?
For now, yeah. Later on, I mean, I'm about to demonstrate why this is going to be tedious to create, because I'm going to have to create the topology. Right? What I mean by that is, let's go ahead and create a binary tree. T is equal to new binary tree, and we'll do this for strings, because that's what these things are. It's technically they're characters, but I'm just going to treat it as single length characters or strings. And we'll go ahead and say that you have this tree node T. I'll call it A is equal to new tree node having the string A. And then I'll do the same thing. Oh, not T, but string. There we go. B, C, D, E, F, G, dot, 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 B, C, D, E, F. B, C, D, E, F. And here I'm only doing this part right here. Here we go. All right, I'll only do this part right here. I'm not going to do the entire thing. All right. But just to demonstrate on how you would actually build the topology with what we've have so far, A is going to be my root, right? Well, that doesn't even impact the tree to create this topology. For example, how do I say that A dot left child, or not get left child, but A dot set left child? What is it? What was its left child? B. What was its right child? C. So A dot set right child to C. There we go. Do I have to set its parent? By default, it's null, right? So that actually brings on a good question here. What are the convenience functions would be nice? Public Boolean has left child. What would that look like? If the left child is not null, then it has a left child. Right child, parent. Has parent. What's another way of saying that it has a parent or doesn't have a parent? Dot has, or dot parent. It's the root, right? If it doesn't have a parent, it's a root, right? So public Boolean is root if, or return this dot has parent. Is that correct though? If I have my parent, am I the root? No. So not has, or not has left child, excuse me. Dot has parent. Right. What about the opposite? What if it's a leaf? Public Boolean is leaf. Return. This dot has left child. I'm going to go ahead and change that logic. If it has a left child or it has a right child, then it is not a leaf. So this is how I would think about it. Right? The negation of that. I am a leaf if I do not have my left child. So if you wanted to, you could go ahead and use, what's that called when you've got a negation and then you distribute that negation? De Morgan's law, right? And what happens to the or? Becomes an and you distribute the negation all the way through. So you can do it like that too, whichever one makes more sense in your mind. I like to think of it without De Morgan's law, and it is not the case that blah, blah, blah. That's just how I think though, right? All right. Well, that sets me up for the left A. What about B? Dot set parent. B's parent is A. Remember that it looks like this, right? B's left child is D and E, and then right. B dot set left child is D, and then B dot set right child is E, right? C dot set parent to A, and C does not have a left child, so it remains null. And F is its right child, so C dot set right child to F. Dot, dot, dot. Dot, dot, dot. Right? Really, really tedious, isn't it? Right? So how would we go about in a structured way of saying, well, I've got all this stuff. I've got A through R. I want to put this into a tree. I don't care about the structure. You handle the structure, right? Tree, you know what you're doing because you're a tree. Go ahead and handle the structure, right? Well, the problem is, what is the structure? So if I have this partially constructed tree here, A, B, and C, right? And I want to insert D. Insert D. Where could I insert it? Well, can I create a third child here? No, because it's a binary tree. Right? Okay, I could put it here. Or I could put it here. Or I could put it here. Or I could put it here. Right? Now, without any further structure, what's the case going to be? Any of those is fine, right? But then that's where you become, that's where you get this kind of thing, right? Without any further structure here, then there's really nothing that we can do. For example, where's that same tree here? There we go. What if I were to try to exploit that kind of binary search on this tree? Okay, let's get rid of all of this. I want you to search for, say, J. Is there any structure here to tell you where to find it? I'll come into A here. Well, that's not it. Do I go left or do I go right? No idea without any further structure, right? Say what?
I was thinking about like something like that. I don't know.
Yep, that's what we'll eventually do. We'll change this binary tree into what's called a binary search tree by giving it a little bit more structure. Before we get there, though, let's go ahead and consider general binary trees here. What is one way that we could go about searching this thing, knowing that there's no further structure? In other words, if this were a regular old list, right, a regular old linked list, how would you go about searching it? You'd start at the head, and then you'd go until you got to the end. Right? But in this case, I have a clear starting point, the root. But which way do I go now? Well, I'm probably going to want to search both ends. So what if I went left first? And then eventually I came back after exploring this entire subtree, and then I came back, well, I didn't find what I was looking for because I was looking for J. All right, well, then I'll go ahead and explore this part of the subtree. Right? That sounds like a recursive kind of strategy to me because you always go left, and then if you're failing that, then you go right. But you have to remember, where did I come from? Right? You need the breadcrumbs to say that, let's see, I'm somewhere in the tree, right? Where did I come from? More generally, let's go with a new diagram here. I'm at my current node, right? Well, did I come from the parent? Or am I returning from exploring the left child? Or am I coming from having already explored the right child, right? I need to keep track of those things. This leads to several different tree traversal strategies that we'll get into here now. Right? How much time do we have? Yeah, we've got time. All right. So just some notes here on the implementation. See the Java class. All right. Basic tree traversals. Right? Unlike a linked list, a tree has two options. It has up to two options at each node, left and right. And of course, you can also return back to the parent. Right? This means that to traverse a tree, you need a traversal algorithm. Right? And in fact, we're going to look at three of them. we're going to look at what's called a pre-order traversal, an in-order traversal, and a post-order traversal. Okay? They're all the same. It's just slightly different on what you do with them. So let's go back to this general diagram right here. So here's my node, U. All right. Actually, no, I'll call it R. All right. Now, don't consider that as the root of the tree. Consider that as the current root, because you can talk about a subtree, right? Let's look at the tree again. Come on. Trees. And binary tree right there. There we go. Just temporarily here. Now, if you look at the entire tree, A is going to be the root. But if you look at the subtree, A's left subtree, then that's rooted at B. And so that becomes the new root if you just focus in on the subtree right here. Likewise, C is going to be the root of the right subtree of A. Right? So you can inductively talk about each one of these things as a root. Okay? There's my root. It potentially has a left child and a right child. What order do I visit these in, or what order do I process each one of these nodes in? Now, what do I mean by process? Well, if you're searching for something, processing would be, here's my key element that I'm searching for. Here's the root element, or here's the node element. Are they equal? If so, success. We're done. We found what we're looking for. Otherwise, processing could mean, all right, we'll take the data out and then send it on to Google Maps or whatever and process it and get an answer back and then print out the answer to the screen or whatever, right? Whatever process means. The process order determines whether or not it's a pre-order traversal, in-order traversal, or post-order traversal. So if it's a pre-order traversal, pre-order, then we are going to go with a root, left, right order. Now, what does that mean? It means that we're right here. This is our current node. We'll go ahead and process R. And then we'll go to the left. Once we're done with the left, we'll go to the right and process that. So root, left, right. If you do it in an in-order traversal, then you're simply just changing where the root is done. You do the left first, then you do the root, then you do the right. Right? So left, root, and right. A post-order traversal is going to be, as you can guess it, you're just going to wait for the root until you're done. Nope, I'm going to wait until I'm done, and I'm going to do the left one first, and then the right one next, and then I'll do the root. So it's left, right, root. Right. Now you might ask yourself, especially if you're put on your combinatorics hat, what are the other options? Left, right, root. Right, left, root, and right. Oh wait, left, right. No, left, right, root. That's post order. Right. Okay, let's start over. All right, so it'll be root, right, left. Then what? Right, root, left. Then right, left, root. Those are the three other permutations. Why don't we consider these? They're just mirror images, right? This one is exactly pre-order, but going right and then left, right? Well, how many folks read right to left in English? Not many. So we always read, again, top to bottom, left to right. These things are superfluous, right? And we like to go left to right instead of right to left. So we're not going to consider those. Right? Now, what does that look like with an actual example? Well, once again, let's go ahead and bring in that binary tree. And let's do a pre-order traversal on this, just to understand what it looks like. Pre-order. Remember, preorder is going to be a root, then left, then right. So I always start at the root. Now, before I visit the left and before I visit the right, I will process A. A gets done first. All I'm doing is listing, enumerating these things. Whatever processing means that's up to you. Right? Where do I go next? I go to this subtree rooted at B. Right? And then I repeat, root, left, right. So it'll be B, then this left subtree, then this right subtree. So B is next. Right? And you can see that I've traversed even more. Right? I'm now down at this subtree rooted at D. So again, I go D, G, H, right? Eventually. So D is next. And then now I'm down here. G. Now where am I? L. There is no left child, there is no right child. So root, left, right, it'll be root, null, null. We ignore those nulls. Now I'm returning from this recursion, let's say. And I've already done G, I did the root, then the left. Now I do the right. Right. I do M, then R, then nothing. So M, R. Now I'm coming back from another level of recursion. Where am I now? I'm back at the one rooted at D. So I go to the right. Now it's going to be H, then left, but there is no left, and then right, and of course no children there, so it's going to be R, H, N. And where I've returned all the way back up to B here. And, right? Yeah, and then so E, predict the rest of it. E, I, O. Right? And then once I've done that, I've returned all the way back up to the top level recursion, and now I take and go do it on the right subtree. I recurse, so I see C, then what? Fast forward mode here. F, J, P, Q, and K at the end. Right? That's a pre-order traversal. I don't believe in saving this. Besides, this is just taken from the book. Oh. What book am I talking about, by the way? Yeah, computer science too. Good. What about in order? In order, I'm going to do the left subtree before I do A. So unlike pre-order traversal, A is going to come after all this stuff, and then in the middle of all this stuff over here. Okay? So I go down to the left subtree here. Do I immediately do B? Nope, that's pre-order traversal. So I go down to this subtree. Do I immediately do D? No, I go down to this subtree, then down to this subtree. And at that point, I have no left child, no right child, so L ends up being the very first node to be enumerated. Then what? Careful. So at G here, I do the left, which was already L. Then I do root G, and then I do the right subtree. When I'm looking at this, R, then M. Right? And now I'm looking at, I'm done with this entire subtree here. So I come back up, and now I do D. And then I do its right subtree, right? Which is going to be H, N, right? Because nothing, H, then N. H, N. Right? At that point, then I come back up to B, right? Again, I've done everything over here, and now I do B. B. Right? Fast forward mode on this part, this part right here. Nothing, E, O, I. E, O, I. Right? And that takes care of this subtree right here. After which, what do we do now? A. And you can see that everything that came before it is an entire enumeration of this subtree right here. Okay? Then what comes after it? Again, fast mode on this. C. Why? Because there was nothing over here, so we didn't enumerate it. Then C. then P, J, Q, F, K. Right. And everything on this side is in this subtree over here. All right. We have plenty of time, so what about the last one? What about a post-order traversal? Each one of these, by the way, has its own applications. Post-order least of all, but we will cover some of those applications. In a post-order traversal, we do left, then right, then root. So tell me what's going to be at the very end here? A. I know that immediately. With a pre-order traversal, what came first? A. Right? The root. All right. So I'm going to do the entire left subtree, then the entire right subtree, and then A at the end. Recurse, or inductively think about this. I'm going to do this subtree here. Well, okay, I do the left, then the right, and then B. So not B yet. Right? So I'm down over here. I do the left subtree, then the right subtree, then D. So I'm going to do the left subtree over here. And now we can probably go into fast mode here. L, R, M, G, right, for this subtree right here. Okay? Then N, then H. Why? Because there is nothing here. Then so we go to the right, and that's N, then H, then D. Right? And at that point, I'm done with this part. Then I do the right part before I do B. So that'll end up being O, I, then E, then B. Right? O, I, O, and then nothing is hanging off of here, otherwise we would have done it. I, and then E. Okay, we're good. And then B. I don't do A, instead I do the right subtree. So fast mode again. P, Q, J, K, F, C, A. It's like an eye test. All right, so that's pre-order, post-order, and in-order traversals. How do we go about implementing them? I kind of presented it as inductively, right? If I'm at a node, what I could do is I could do some sort of a recursion. Do the left, or if for a pre-order traversal, I'm at a node, process it. But then make a recursive call to the left subnode, make a recursive call to the right subnode, and take care of the recursion, take care of the processing in the recursion. What's an alternative to recursion? What kind of a while loop? We're using what kind of data structure? So the idea here is that I needed to keep track of my breadcrumbs, right? Where did I come from? So that I know, oh, well, in a pre-order traversal, for example, what did we end up doing? We came all the way down. Down, 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 down. Right? I needed to remember that on your way back up, you still need to go to all these rights over here. Right? To do that, I needed to keep track of where I came from. I came from A, then from A I went to B, then to D, then to G, and now I'm at L. Excellent. A stacked data structure will help us keep track of all those breadcrumbs as we go down. Right? Or we could do recursion. In either case, I'm going to have to build this example here, and then when we come back, I've already got it pre-built somewhere else, don't worry about it. But when we come back on Thursday, then we can start implementing these algorithms. All right? All right, any questions? No? All right. Then have a good rest of your day.